everyone. This lesson is going to be about vector calculus. So we're going to do 3 questions here. The first one, we've been given the position vector r in a parametric equation in terms of t, and we need to find the velocity. So for part A, we will note that the velocity of a particle as a function of time is the time derivative of its position vector. Now, sometimes you'll see that denoted, instead of velocity, sometimes you'll see that as r dot. R dot is meaning just a shorthand way of saying the first derivative. I don't really like that notation. I think it's too easy to mistake a single dot for something else. So I prefer to write velocity instead of r dot, but you may come across that. Now let's go. We need the derivative first of 3 times t squared. So that is 6t, and that would still multiply by I hat. Then we need the derivative of 4. 4 is a constant. The derivative of a constant is 0. So it's plus 0j. I'm not even going to write that. That's the velocity vector. Now part B, we want the acceleration. So acceleration as a function of time, that is the time derivative with respect to time of the velocity. Now again, you might see this written as r double dot. So we're familiar with the idea that a derivative of a derivative is called a second derivative. The notation also exists that you can call it r double dot as a second derivative. Once again, I don't like that notation. I think it's too easy to get mixed up. So I would prefer to write v for velocity, a for acceleration. Much clearer in my opinion. Now we're taking the derivative of this function with respect to time. The derivative of 6t is 6, and that would be in the I direction. There was no j or k component. That's it. That's the acceleration. Finally, find the velocity and acceleration vectors at t equals 2 and describe the motion. So for part C then, to find the velocity of the particle when t equals 2, we literally substitute 2 for t. 6 times 2, that's 12i. And there was no units given here. I'm going to assume SI units of meters per second. The acceleration vector when t equals 2, well, there's no dependence on time. It's not like it's 6 multiplied by anything. It's just 6. So it is literally a constant acceleration. It wouldn't matter whether time was 2 or 5 or 7. The acceleration is 6. It's a constant acceleration. And that's what they're talking about describing the motion. It is a constant acceleration. Now, as far as describing the motion, we could do the trajectory. They didn't ask for that. I believe it would be a linear motion, but we'd have to do the Cartesian equation for that one. Anyway, that's the end of question 1 there. Let's go across to question 3. So this time they gave us the velocity of a particle. You see how they've written r dot there? It's very easy to miss that little dot. So that's why I don't really like the dot notation very much. So be careful when you're doing these. R dot, or velocity, given by this vector. Time is in seconds, distance is meters. Now they tell us when t equals 0, the position vector is here. This would be the original position, r naught. Find the position at time t, given that it begins from, well, now that's contradicting the previous line, isn't it? How can it be at this position when t equals 0, and how can it be at some different position? I'm going to ignore that as if it's some sort of a horrible mistake and go with what was in the original stimulus for the question. There's definitely a problem with this question, the fact that the particle seems to start in 2 different places. That's physically impossible. So here we go. Now we've been given a velocity. We know that a velocity vector, and remember r dot velocity, we know that is the derivative of r with respect to time, don't we? So I'm going to multiply. I will have v as a function of time dt equals dr. Now the way to solve this is to do the integration. So I'll replace vt with this formula 5ti minus 2tj. So I need the integral of 5ti hat minus 2tj hat. Still dt there, meaning we're integrating with respect to t, the time variable. And remember, the integral of d something is just that thing, it's rt. So now we integrate 5t with respect to time. So the 5 will still be there. The power on the t increases to a 2 and we divide by the new power, and that multiplies by unit vector I. Subtract, now the 2 will still be there. The t was a power of 1, it increases to a power of 2 and we divide by the new power. Now that will cancel, but that's for the j component. And don't forget, we have a constant of integration. And because this is a vector equation, our constant will be a vector. So this is the point where we need to use the clue here. Now this is called the initial conditions. So t equals 0 at the start, r equals this. So we will substitute that, and I'll make a little note. Need my normal pen back. We will substitute t equals 0, and they literally told us that the vector for r is 3i take 4j. 3i take 4j. So let's substitute that into the equation we've got sitting there. So I would have 5 over 2 by 0 squared I minus 0 squared j plus c, my constant of integration, and at that the r vector is 3i take 4j. There it is, 3i take 4j. Well, that's nothing, and that's nothing. It looks like my constant is 3i take 4j. So I will then rewrite my equation here. Just let me label that as equation number 1. So from equation number 1, the position vector as a function of time is 5 over 2 t squared I take t squared j. Instead of plus c, I will write plus 3i take 4j. And then we normally write this more neatly. I'll group together the I components. So I'll have 5 over 2 t squared plus 3 I. And then I will have, now see how it's subtracted there? I normally write plus, and so it will be negative t squared take 4j. Now some people may prefer to factor the negative sign to the front, so subtract, and then it'd be positive t squared plus 4. But either way is good. That is my solution to part A. That is the position vector of this particle as a function of time. And we started with a velocity vector, and we performed an integration to solve that. Now it is find the acceleration at time t. So the acceleration, of course, is the derivative of velocity. There we go. This is a little bit like one that we did in question 1. The acceleration is the derivative with respect to time of a velocity function. Now the velocity function was 5t take 2t, 5ti take 2tj. Let me write that down. 5ti take 2tj. That's the velocity function. So this is still the derivative of this thing. So the derivative of 5t is 5. And the derivative of negative 2t is negative 2. Once again, our acceleration here Even though it's acceleration as a function of time, there's no t appearing in this equation, so this is a constant acceleration this time. Just like we had in the previous question. There's no value of t in the formula for acceleration. Final step is sketch the path of the particle from t equals 0 to t equals 3 and describe the motion. Now, to sketch the path of the particle, we could literally find the position vector for t equals 0, 1, 2 and 3, then plot the points at the end of those vectors and connect the dots. I'm not going to do that for you because that's a pretty straightforward thing which we've done before. The main point of this one was how we use integration here to go from a velocity back to a position, and the need to do the initial conditions here to evaluate the constant of integration. There is a third question. Here we go. We've been given an acceleration this time, and the particle starts from this location, so that's a position, with a velocity, that's initial position and initial velocity. I'll just write down here, this is r naught, and this is v naught. Find the position and velocity at any time. Okay, so here we go. We know that the acceleration as a function of time is the time derivative, whoopsie, is d over dt, the derivative with respect to time of velocity. Good. So we will start from this. Now I will rewrite this. I'll put the v as a function of t over here. There's a d in front of that, d, that. Now there I'll put the a, acceleration as a function of time multiplied by dt over here. I'll integrate both sides of these. The integral of d something is that thing, that's a vector, velocity as a function of time. And I need the integral of acceleration. Acceleration was 12t, I take 9j. 12t, I take 9j dt. So the 12 will be there. T will become t squared, and we will divide by the new power, that's times I, minus 9, and the integral of 9 is 9 times t, and there's a j there, plus a constant of integration. This is velocity as a function of time. That would cancel more neatly to be 6 times t squared. Now we will substitute, or we will use the fact that v naught, the initial velocity, was 4i take 2j from up there. 4i take 2j. So if v is naught, so here we go, v naught equals that, and that really means I could put 0 for time, and 0 for time I'd have 6 times 0 squared I minus 9 times 0j plus vector c. Well, that's nothing. It looks like my constant is 4i take 2j. So rewriting the velocity function then, I've got 6t squared I, and then I'd have another plus 4i. So it's really 6t squared plus 4i. Then I have the subtract 9t, then I have subtract 2. So I'll add on this bit, negative 9t subtract 2j. And there's our velocity function. Now, the video is getting a little bit long, so I won't continue. That's just the first step, where we've gone from finding using the acceleration and then doing the integral, using the initial velocity to find the constant, and then writing our formula for velocity. We would do the same process again. We would integrate this one to get the position vector. So just like we did over there, we started with a velocity vector, and we integrated, and we ended up with a function for position. So that's a quick introduction to a few of the steps that you'll need to solve these problems today. Thanks for watching.